All right, welcome back, focused learners. Today we're tackling the actual blueprint of digital trust. If you're gearing up for your Security Plus exam, or honestly, if you just want to deeply understand how data stays locked down on the modern internet, you are in the perfect place. We're going to build your understanding of digital trust right from the absolute ground up.
Okay, let's dive into this. Here is our roadmap for today. We'll be hitting 5 main sections. First, the foundation of hashing. Second, fortifying passwords with SALT. Third, key stretching and pepper. Fourth, the power of digital signatures. And finally, number 5, how digital signatures work.
Section 1. The foundation of hashing.
Now, understanding hashing is literally the absolute baseline for verifying that our digital data hasn't been maliciously or even accidentally tampered with. And listen, here is a classic exam trip-up, and honestly, a super common real-world misunderstanding. People constantly mix up encryption with hashing, but look at the stark contrast here. Encryption, that's designed to protect your data while it's in transit. Hashing, on the other hand, is a one-way function. Its primary job is authentication. It basically acts as a checksum to verify that files are entirely unaltered. They're two completely different tools for two completely different security goals.
So how does this actually work under the hood? Let's walk through the mechanics of a hash algorithm step by step. First off, because messages are almost never the exact perfect size an algorithm needs, we apply something called padding. This divides the entire message into fixed-size data blocks. Take the SHA-1 algorithm, for example. It takes blocks of exactly 512 bits. Second, the hash function runs through multiple rounds. In SHA-1, that's 80 rounds per block. And here's where it gets incredibly clever. The output of the first data block is actually fed right back in as input along with the second data block. Finally, step 3, it outputs a fixed length value. If you use SHA-256, it's going to output a 256-bit, 64-character hex string every single time. Doesn't matter if your original message was a 2-word text or a massive database.
And this brings us to something that brilliantly illustrates the avalanche effect. You absolutely want to make sure this key vocabulary sticks in your mind. The avalanche effect is this dramatic phenomenon where changing just one single bit, anywhere in a message, causes the entire resulting hash value to change completely. Just think about that for a second. You change one tiny character in a massive file, and the final 64-character output becomes totally unrecognizable from the original. That dramatic shift is exactly how we prove our data was messed with. But what happens when the math actually fails us? Well, that brings us to a collision. A collision happens when two completely different files produce the exact same unique hash value. For a hashing algorithm, this is absolutely catastrophic. It basically renders the whole system useless. Imagine you write a software script, right? You hash it before adding your digital signature, and then you hash the whole package again so users can safely download it. But if an attacker's malicious file produces the exact same hash as your totally safe software, the user's computer thinks that malicious file is yours. Boom, the trust is completely broken.
Section 2. Fortifying passwords with SALT.
So, we've built a solid foundation with hashing, but as we just saw with collisions, foundations can be cracked. As attackers get more and more sophisticated, we need serious reinforcements. Which leads us to pivot over to password security and ask a really high-stakes question. How do we actually protect passwords in storage from being easily read or cracked? Because if we just use simple hashes, attackers have long since figured out ways to reverse engineer those.
The elegant answer here is salting. Salting is simply the addition of random data to a password right before hashing it. We have to remember that historically, passwords used to just be stored in plain text on a system. Anyone with access could just pull them up and read them. Adding this random data, this salt, became a massive, crucial safeguard for passwords sitting in storage.
The really crucial point is just how much heavy lifting this simple addition does. First, it defends against pre-computed hash attacks, like rainbow tables, where attackers come armed with massive lists of pre-hashed passwords ready to test against a database. Second, because salts are totally random, they inflate the required hash table size, making it prohibitively massive for an attacker to compute. Third, and this is huge for daily usability, it protects users who insist on using super common passwords or reusing them everywhere. It ensures that multiple instances of the exact same password look completely different in the database. And best of all, it provides all this protection without placing any extra memorization burden on the user.
Section 3. Key stretching and pepper. We're kind of leaning into a culinary metaphor here, as you can probably tell. We're going to add some more ingredients to our password recipe to make it even harder for attackers to digest. Now, what's really interesting is how these 3 elements combine into what we call a key derivation function. Think of this as your master recipe. You have your password, right? That's the base ingredient.
You add your salt, which is that randomly generated additional input we just talked about, and then you add pepper. Pepper is a randomly generated secret salt that is kept entirely hidden on the system itself. Combining these three ingredients in a key derivation function creates a ridiculously robust key that thoroughly thwarts brute force attacks.
We call this overarching process key stretching. Key stretching fundamentally increases the time and space resources needed for a computer to test each possible key. It slows the attackers down. However, I do have to caution you about one very specific edge case here. While key stretching makes a weak password much stronger, if it's applied to a top-level key or a password that is already extremely long, it can actually result in a shorter and less secure key. It's a rare exception for sure, but definitely an important one to know.
Section 4. Power of digital signatures. All right, we are at the climax of our digital trust narrative now. We're taking all these cryptographic concepts and applying them to prove not just what the data is, but exactly who sent it. A valid digital signature is incredibly powerful because it guarantees 3 specific things. Definitely use this rule of 3 for your studying. Number 1, authentication. You know with absolute certainty who the sender is. Number 2, integrity. You know the message was completely unaltered in transit. And number 3, non-repudiation. The sender cannot possibly deny signing it. These 3 guarantees clearly lay out exactly why digital signatures are the absolute gold standard for things like software distribution and high-stakes financial transactions.
Let's break down that heavy vocabulary word for a second, non-repudiation. The real-world stakes here are all about undeniable proof. This means the signer cannot successfully claim they didn't sign a message while at the very same time claiming their private key remains a secret. You just can't have it both ways. And to make it even more secure, some non-repudiation schemes use a timestamp. That means the digital signature remains completely valid to the exact time it was signed, even if the private key gets exposed or compromised somewhere down the line.
Section 5. How digital signatures work. So, we know what they achieve. Let's move to and see how this builds. Let's look at the actual underlying mechanisms here. Digital signatures employ asymmetric cryptography to provide a layer of validation to messages sent through non-secure channels. I really want to remind you here that it's these properly implemented cryptographically based schemes that make these signatures incredibly difficult to forge. The math is literally doing all the heavy lifting to secure our communications.
Let's step through the 3 algorithms that make this happen, and we'll take it slow, using the NIST digital signature algorithm, or DSA, as our primary example. Step 1 is key generation. The algorithm selects a completely random private key and then outputs a corresponding public key. Step 2 is signing. The algorithm takes the message itself, along with that private key, to produce a unique signature. And finally, step 3 is verifying. The receiver uses the original message, the sender's public key, and the signature to either accept or reject the authenticity of the whole message.
This entire system relies heavily on 2 mathematical guarantees that make the asymmetric system functional and trustworthy. First up, authenticity generated from a fixed message and a private key can be definitively verified by the corresponding public key. And second, generating a valid signature for a party without knowing their private key is computationally infeasible. Without the key, the math just straight up won't let you fake it.
To connect all this abstract math back to reality for a second, consider this quote. As organizations move away from paper documents with ink signatures, digital signatures can provide added assurance of the provenance, identity, and status of an electronic document and can also be used to acknowledge informed consent. We are experiencing a massive shift away from pen and paper contracts right now, and these cryptographic algorithms are essentially our new ink.
So I'm going to leave you with this final provocative thought. If a single changed bit avalanches a hash today, and a secret pepper stretches a key to stop brute force attacks, how will these intricate layers of math evolve as quantum computing threatening to crack our digital trust tomorrow? The future of cryptographic solutions is moving incredibly fast, and the stakes have literally never been higher. Stay curious, keep focused, and I'll see you in the next explainer.